The cornerstone of efficiency in multi-layer switches, in Cisco multi-layer switches, is Cisco Express Forwarding. At its fundamental, the Cisco Express Forwarding, or the CEF as Cisco calls it, is a set of functions and tables that separate the operations on the multi-layer switches into distinct control plane operations and forwarding plane operations. And to do that, they enlist help of several different tables, like the routing table, the forwarding table, the adjacency table, which is, again, very, very important table in Cisco Express Forwarding. And then all this comes in different flavors, implemented differently on different devices. So these are the things that we are going to talk about next. One of the most important concepts when we are trying to understand Cisco Express Forwarding is the separation it creates between the control plane on the device and the forwarding plane on the device. Now, if you're unfamiliar with these terms, better start getting familiar with them, because when you start exploring concepts like, for example, multi-protocol label switching, MPLS, or any modern advanced networking technology, this separation of control and forwarding functions becomes very, very important. So let me try to explain what that is. And to do that, I'm of course going to go to my handy whiteboard here. Imagine that we have a network consisting of several devices, but the device that we care about is the multi-layer switch, or the router that we have here. And let's say that this router has two interfaces. Let's call this interface 00, whatever type it might be. So let's say that it is fast Ethernet 00. And on this side, we have fast Ethernet 01. And we have an incoming packet. So this is not layer 2 operation that I'm talking about. This is going to be a layer 3 operation, the routing of this packet. And let's say that what we know as users is that this incoming traffic here, so this IP packet that we have, needs to go through this router here, and it needs to be sent out of this particular interface. Now, when this packet arrives on this interface here, there are certain things that need to happen inside this device to allow this packet to be switched across. Generally speaking, what we need to do is we need to take a look at what was the destination IP address of this IP packet. We need to look it up in some sort of a database. And based on information from that database, we have to make a determination. We have to make a decision that this packet needs to go out of this interface towards a particular next hop that has a certain layer 2 address. So we need to include layer 2 encapsulation in the process. On Ethernet, this layer 2 address is most likely going to be determined using the Arp table or using the Arp protocol to find out what the layer 2 address of this layer 3 packet needs to be. Now, all these processes here need to happen for pretty much every single packet that goes through. So in traditional IP routing, this process was relatively slow. Now, I should maybe put slow in air quotes here, because what is slow or what is fast? But I should say this process used to be very inefficient. Take a look at this. So we have an incoming packet. This incoming packet, we needed to take a look at the destination IP address, so we needed to extract that information from that packet. We needed to perform the lookup in the routing table to find the best match. So we needed to go through the list of all the routes that are there and find the route, the destination pattern that matches this IP packet the closest. Once we have that, we have to determine what is going to be the exit interface. Exit interface is simply the interface where we need to send the traffic. In our case, this is going to be fast Ethernet 01. So once we have the route, once we have the exit interface, we had to resolve the next hop information. In other words, we have to figure out what is the next hop for this route. And then we needed to find what is the layer 2 information for this next hop. And this involved multiple lookups in multiple databases. For example, this here would be a lookup in the routing table. The exit interface could also come from the routing table, but it could also come, for example, from the Arp table or from any other table that we might have on our router. Resolving the next hop could also be done in the routing table. It could also be done in the Arp table. And the layer 2 information was done using the Arp table here. And imagine a lot of this traffic. For all of this traffic, we needed to perform all these lookups. Even if we had to do only this, it would have been relatively inefficient, because for every single packet we would have to consult the routing table. Cisco recognized in their past that this is not a very efficient process, and Cisco has tried to address this issue using many different historical solutions. One of these solutions was to use something that they called the net flow switching, where only a first packet in the flow would be sent towards the routing engine on the device, and then based on the routing decision made for that first packet in the flow, we would program the layer 2 databases on the switch so that all subsequent packets in that flow could be switched the same way. But this was terribly inefficient, because if we had a high rate of this traffic arriving, what would the second packet have to do? We would either have to drop it or we would have to delay it, which would in both cases produce undesirable results. If we had to drop subsequent packets while the resolution of, for example, Arp table is going on, what is going to happen is we are going to have high drop rates of the traffic. If we delay the traffic, that means that we had to have large input buffers, which means that we would have to have larger memory, and with larger memory we would have more expensive devices, and not to mention that at the same time we would be increasing the delay for the traffic going through our devices. So this first attempt at multi-layer switching that Cisco attempted wasn't very efficient and wasn't very successful. But at the same time, in a parallel business unit in Cisco, in the routing world, Cisco was developing this Cisco Express forwarding cache, that, as they call it. Now, the basic idea behind Ceph cache is that we are going to build a table from all sorts of different databases that we might have that is going to contain all the information that we need to successfully forward the packet. So I'm not talking about switching the packet, I'm not talking about routing the packet, I'm talking about forwarding the packet. Now, you may think that these are just semantics, but this is actually very, very important concept. Why is it important? It's important because when we say switching, we somehow immediately in our heads imply, okay, this is a layer 2 information only in use here. If we say, oh, the packet is being routed, we are immediately going to be thinking, oh, there needs to be a routing table involved here, and we need to perform the lookups in our routing table. So this is why we are opting to use this third term, even though technically speaking, all these are really synonyms to each other if we take strict meaning of them, but forwarding the packet actually implies that we might be using information from all these different databases, that we might actually be using information from our routing table and from our Arp table and from any other database. But in order to use that efficiently, we may need to have a separate database that might be a little bit more efficient. What if we had a way to look all this information up in a single database instead of consulting multiple databases to build our forwarding table? And this is exactly what Cisco did when they implemented Ceph. They created a forwarding information base, or the FIB, which is basically a database that contains information about routes. It contains information about next hops. It contains information about layer 2 information for next hops, and some other pieces of information that may have to do with security, like access lists, for example, or the QoS, for example, so that we know which QoS markings to put on our packets or frames that we are generating as the result. And this separate forwarding information base is what we are using when we are talking about the forwarding plane on the router. Now, let me show you what is the relationship between different databases in a Cisco switch. When we are talking about forwarding of traffic in Cisco switches, as I said, we have to think about two separate processes on the switch. We have to talk about the control plane processes, and we have to talk about the forwarding plane. In the control plane, we have the database that we call the routing table, or the route information base, or RIB, or the RIB. And this database is built using all sorts of different routing protocols. And then we have the connected routes. We have static routes. And whatever information we can use to actually generate the routes that we can see with show IP route. So if we wanted to see the information in our route information base, we would run a simple command, which is show IP route. In the control plane as well, we have our Arp table. Arp table is built using the protocol that we obviously call Arp. But we can also have static entries in our Arp table. We can statically program information that is contained in the Arp table. These two databases are sitting in the control plane of our device. Sometimes this control plane of our device is called the layer 3 engine, or is sometimes called the route processor, or RP. Or sometimes it is called the route engine. There are many different names for pretty much what is control plane. Now, based on this information that we have in our routing information base and based on the Arp table, what is going to happen? These two databases are going to feed our forwarding information base, our FIB, which is basically a Ceph table. So let me just write somewhere here. This is basically our Ceph table here. And in the FIB are going to be all the routes with their resolved next hops. But these resolved next hops are actually going to be kept in a subset table, which is called the Adjacency table, where for every single destination, we are going to have an information about what is the resolved next hop for this destination. Now, these databases here can be observed. So Arp obviously can be seen with show Arp. And we can observe information in the forwarding information base in the Ceph table with show IP Ceph. And there are some other commands here that we can use, and we can observe the information in the adjacency table using the command show adjacency. And let me now show you some of this information in action. And as usual, I'm going to make these things very, very simple. I'm going to build a relatively simple network consisting of a single switch, and this is going to be my Cat1 switch. And on this switch, I'm going to create 3 SVI interfaces. I'm going to create interface VLAN 12, VLAN 13, and VLAN 14. And these SVI interfaces, and as you might remember, SVI interfaces are those logical interfaces that don't actually relate to any physical interfaces directly. I'm going to have several devices connected behind each one of them. So on my VLAN 12, I'm going to have 2 devices connected, and they are going to be on 192.168.12.0/24 network. So I'm going to have device that ends that has last octet 220, and on this side I will have .1. In my VLAN 13, I will have a similar setup. I will have device with 3 and 30, and this is going to be 192.168.13.0/24. And here for VLAN 14, I'm going to have a similar setup with 4 and 40, and this is going to be 192.168 14, 0/24. And what I want to do here is I want to observe my rib, fib, and adjacency tables on Cat1. I have built my network in the meantime, and all I have to do now is observe these different databases. Let's start with observing the routing table first. I'm going to do show IP route on Cat1, and what I'm seeing here is that I have 3 connected routes. I have 192.168.12.13 and 14 directly connected to interfaces VLAN 12, 13, and 14. So this information here is what I have in my rib, what I have in my routing table. If I run the command show IPsef, what I'm going to see here is I'm going to see the contents of the Ceph database. This is the content of my fib, of my forwarding information base. Now, let's focus on information that I can see here for VLAN 12. And you can see here that I actually have quite a bit of information for VLAN 12. I not only have a single entry, I actually have 4 entries for it. The first one that I see is one that I might expect to see. I can see 192.168.12.0/24, and it says here that the next hop is attached. This basically means that for this adjacency, for this particular network, I might need additional information to send this traffic there. This is what attached means. So here I'm going to probably need help from Arp to actually find out what the information there is to send traffic directly there. Now, for these 2 entries here, or actually these 3 entries here, I actually have a receive next hop. This means this is this device. Now, this device, as we know, has this IP address configured, but remember that 0 in this case is the network address, and 255 is the actual broadcast address for this network. So traffic sent to this address, or this address will be actually processed by this device itself. It is going to accept this traffic, it's going to receive this traffic, and it's going to process it. But let's take a look at the adjacency table. So if I do show adjacency, what I'm going to be seeing now is pretty much nothing. If I do show adjacency summary, which is another command that I can run, it is going to show me that I actually have 0 adjacencies. Now, this may not be the case, you may be thinking, don't I have some hosts behind here? Well, I do, but Ceph doesn't know anything about them. Remember, the Ceph table is built from the information coming from the routing table, and we have that information, and it's also built from the Arp table. So these 2 databases are going to feed our forwarding information base. Did we even look at the Arp table up until now? Well, let's take a look at Arp table. If I do show Arp, I'm not going to be seeing anything except my own IP address and my own MAC address for VLAN 12 here. This is why the adjacency table is empty, why I don't see anything in the adjacencies. Remember, those adjacencies that we have seen, those direct adjacencies, those received adjacencies, those that are connected directly, so not connected, those that belong to this device itself, they are not going to be in the adjacency table. It's this device. It's not adjacent information. It's not a device adjacent to this device that we are observing. It is actually this device. So let's now make something go into our adjacency table. How can I do that? Well, very simple. What I'm going to do now is I'm going to ping 192.168.12.2, and I'm going to send 5 pings, which is the usual for iOS. And I will see that after 1 or in some cases maybe 2 packets are going to be lost until ARP actually works its magic, I'm going to have successful ping. At this moment, I actually do have information in my Arp table. So now I can observe that for 192.168.12.2, I actually do have a MAC address here in VLAN 12 interface. So at this moment, if I do show adjacency, what I'm going to be seeing is that I actually do have an adjacency with a host that has 192.168.12.2 address in VLAN 12. Let's take a look at this in more detail. So what I'm going to do now is I'm going to run the command show adjacency detail. And here I can see all sorts of interesting information. The first thing that I'm seeing here is the IP address of the host. This is something that we have expected to see. This is how much traffic was actually Ceph switched towards this destination. And mind you, these counters are probably going to be empty for traffic that is generated by this device. This is going to be only for Ceph switched packets. And the next thing that we are going to see here, epoch basically in Ceph terms means what is the version of the forwarding table. As the information is updated, and this is mostly important when we have high availability devices that may have multiple routing engines, multiple routing processors, and one of them fails, and when we have an NSF switchover, when something else takes over, we need to see what is the copy of the forwarding information base that we have, and we may need to update and age out older information. But in other circumstances, the epoch actually is not giving us any real true valuable information. It's mostly important in those high availability scenarios. So this is not at this moment information that we are interested in. But what is interesting is this long string of characters here. Now, this long string of characters actually consists of the destination MAC, source MAC, and protocol to use. How do I know that? Let me show you. All these numbers here are hex numbers, which means that every pair of two numbers signifies a single byte. So if I count 6 bytes, so here is the first boundary. Let me clean this up and show you. So this is where the first boundary is. And then again, let's count 6 bytes. 1, 2, 3, 4, 5, 6 bytes here. And then finally, I have ether type at the end. And as we know, ether type 0800 signifies that this is an IP packet. So here we have the destination MAC address. And here we are going to have the source MAC address that we need to use to send the traffic here, which is basically going to tell us what is going to be our outgoing interface. Let me show you this. So if I do show ARP here, and if I take a look at 12.2, this is the information that I'm going to be looking. So I'm looking for 00190617, 00190617, 5AC1. Look, this is it. So this is going to be our destination MAC address. Let's look at the source information here. So this is the one I'm looking at. So if I do show interface VLAN 12, this is the, let me scroll this up a little bit so that we can see it. So this is the source MAC address, or this is the MAC address that is in use by VLAN 12. And let's compare it with this value here. So I have 001906, 001906, 0C, 0C, here it is, 5EC1, 5EC1. So this here is going to be VLAN 12, and this is going to be the destination MAC address that we are going to be using to send these packets out. And these are going to be the IP packets, and I can clearly see that because I have the ether type to use here. And this is very, very interesting. Another information that we have here, so let me go back and do show adjacency detail, is how did we learn this information? And here we have information that this was learned from the Arp table. So at this moment, we have information in the RIB, we have information in the Arp table, we have seen information now in the adjacency table. So let's take a look again into our Ceph table. Let's see what are the contents of the Ceph table now. So if I do show IP Ceph, now I'm going to see that I have this entry here. Now mind you, I still have this 192.168.12.0/24 that is attached, but now I have 2/32 that is also attached to VLAN 12 interface. Let's take a look at this entry in a little bit more detail. So here I can do show IPsef 192.168.12.2/32, and if I just press enter just like I did now, so this was the command that I ran, I'm going to see information this is attached to VLAN 12. That doesn't give me much information, but I can always append the detail. Now, with the detail information, I can see here that this is really a child of this entry here. It's more specific entry than this one. I can see, just like before, that this is directly attached to VLAN 12, but what I do have here is the IP address that we are using. The attached adjacency is by far not the only adjacency type that Ceph recognizes. Another important type of adjacency that we can observe in Ceph is called the Glean Adjacency. Glean Adjacency is, in most cases, attached adjacency for which we are missing some piece of information. Like, for example, a transient state when we need to send the packet towards a certain destination. We have the route for it, so we have an attached adjacency, but we don't have an ARP entry for a specific host that we are trying to send to. When a certain destination is in a Glean adjacency, we unfortunately have to drop the traffic until that Glean adjacency has been resolved. This happens relatively quickly, but this is the reason why we are from time to time going to see drop in our traffic. It's usually just one packet that gets dropped. Another important adjacency is called the null adjacency. Null adjacency is the traffic that is destined for a null interface. A null interface is a bit bucket drop interface on a router that simply drops the traffic that goes to it. Drop adjacency, while being very similar to the null adjacency, is somewhat different. The drop adjacency is adjacency that drops the packets just like the word says, but they are not caused by the traffic that is destined towards the null adjacency. Semantics, you might say. Discard adjacency, on the other hand, is a little bit more complicated. Why more complicated, you'd say? Well, you see, we have three types of adjacencies, null, drop, and discard, that have the purpose of simply not forwarding the traffic. The discard adjacency is the adjacency that discards the traffic as the result of a certain feature being configured that discards the traffic. Like, for example, an access list applied on an interface. So the drop interface is dropping the traffic as the result of something not quite being right. Like, for example, the incorrect protocol header in the traffic, or the interface suddenly going down and we lost the adjacency that we had at that very instant. That suddenly becomes a drop adjacency. However, the discard adjacency is a purposeful discard, drop of the traffic, purposeful rejection of the traffic that we have actually configured. And last but not the least is the punt adjacency. Punt adjacency is adjacency in which, unfortunately, Ceph cannot directly forward the traffic. For punt adjacency, we need to send the traffic back to the control plane. We need to send it to the brain of our device. We need to send the traffic towards the route processor. This happens when certain flags have been set in IP packets, like, for example, the router alert, or we have a receive adjacency, the traffic that needs to go to the router itself. This traffic, we say, is being punted. Just like a ball in American football, we are punting this traffic towards the routing engine for forwarding. And the last thing in this segment that I'm going to talk about is going to be different Ceph flavors. Ceph comes in, as the word implies, different kinds of operation. A relatively simple Ceph is on a fixed configuration switches, like, for example, 3750 series or 3560 series, X or non-X, it doesn't really matter. Now, I say relatively simple implementation because there we have a single routing engine and we have a single, I should say, line card that forwards the traffic. But on more complex platforms, like for example on 4500 series switches or 6500 series switches or 6800 series switches, what we have there is a possibility of so-called distributed forwarding. Now, distributed forwarding is an idea that we can have a copy of Ceph not only on the supervisor module, on the brain of the switch, but we can have a copy of the Ceph on the individual line cards themselves. Let me try to explain this in a little bit more detail. When we have that situation, we may have a chassis that has a supervisor module that has the routing engine or the route processor. And then we may have different line cards. So let's say that this is line card 1 and this is line card 2. And on these line cards, we may have, for example, 48 ports, and on this one we could have 48 ports. And we could have a copy of Ceph table transferred from the supervisor module, from the centralized forwarding card. We could have this information sent to individual line cards. Now, what that allows us to do is when we have traffic that arrives on, let's say, one port on a line card here, and that it needs to go out of this port here, what we can do is we can perform the forwarding of this traffic directly in the line card without actually sending this traffic down to the fabric and having it switched back out of the same line card. So in this case, we are saying that we are using distributed forwarding, or in other words, that we are using distributed Ceph, or DCEF, as Cisco calls it. This idea of distributed Ceph does create certain challenges that may need to be overcome. For example, are line cards using the same copy of the Ceph table? Are we using redundant supervisors, in which case we have supervisor 1 and we may have supervisor 2 that also has a copy of the Ceph table? So which one is active? Are we using an active-active setup, which is not very common these days, but I remember a long time ago we did have active-active supervisors, and that was one terrible mess, I can tell you about that. Or we are using non-stop forwarding. Non-stop forwarding is a situation in which we could have a supervisor, an active supervisor, fail, while the line cards are still performing the forwarding because they are using distributed Ceph. But then when the redundant supervisor kicks in, it actually needs to overwrite that information. And you might remember that just a couple of minutes ago, I did mention that Ceph epoch does help with this, because this is simply a revision number of the forwarding table that we have. But these are relatively advanced topics that you are unlikely to encounter in any of the current Cisco exams.